What's going on, everybody? It's Mr. Gus, and I'm in the physics conference room. You may have just come from the right-hand rule for charges videos. Now we're going to do the right-hand rule for current carrying wires. So it's still a qualitative video. We're talking about qualitative things here, but instead, this time I want to talk about the magnetic field produced from a current carrying wire. So if I have current running through a wire, that's a bunch of charges. Charges move. If charges move, charges produced through a wire produce a magnetic field. And so the question is, well, how do I know the direction of the magnetic field? How do I know what that magnetic field is, the direction it's in? How can I do that? Well, it's still our right hand. We're using right-hand rule to figure out the force on things. Some people call it the first right-hand rule. And when I'm trying to figure out the magnetic field around a current carrying wire, I also use my right hand, and some people call this the second right-hand rule. So let's talk about it. The thumb still shows the direction of current. That is still part of our right-hand rule. That doesn't change, okay? But when I'm talking about a single object, a current carrying wire, there is no force. Right? In order for there to be a force, I need two different current carrying wires, or a charge and a magnetic field. I need always need two different objects to interact in order for there to be a force. You cannot have one object apply a force on itself. It just doesn't work that way. That's not how forces work. Forces are an interaction between objects, a push or a pull. So for the second right-hand rule, for a current carrying wire in the direction of the B field in a current carrying wire, we need our right hands again. Now, thumb is still the direction of current. The cool thing with the right hand, though, is that our fingers can wrap around things. So the way we're going to do this is the thumb is going to point in the direction of the current, and the way your fingers naturally curl will show you whether or not that current, or that B field, that magnetic field, is the direction it wraps around that wire. Let me give you an example. I got three over here. So the first one, my current flows up the page. So I take my right hand, I point my thumb up the page, I take my fingers, and I wrap my fingers around that wire. And when I do that, I see on this side of the wire, my fingers are into the page, and on this side of the wire, my fingers come out of the page. And that's exactly the way the magnetic field aligns itself. So over here, I would say I'm into the page. And over here, I would say I am out of the page. That means anything on this side of that wire would have a magnetic field out of the page as a result of this wire. And anything on the right side of this wire has a magnetic field into the page as a result of that wire. Let's try the next one. They're independent things. The next one, I've got my current. Now my current is traveling down the page. Because it travels down the page, I would wrap my fingers naturally into the page over here, out of the page over here. Let's draw that magnetic field. There we go. Now, I can also have a loop of wire where a current comes in, it loops around, and then loops itself out. That would be a way for me to show a loop of wire. Well, let's see what happens here. As I enter here, I can see my current on this side is moving to the right. So as it moves to the right, my fingers are into the page, out of the page. So over here, I would say into the page over here, out of the page over here. And as I enter into my loop, you see my thumb. In this case, the current's moving upwards this way, leftwards, downwards. My current moves up. My fingers are into and then out of. So outside of this loop of wire, my magnetic field is out of the whole time. The entire time I am into the entire time, which means inside this loop of wire, that magnetic field is moving outward at me the entire time. And then as I exit the magnetic field, I would see a different thing. But inside that loop of wire, I am getting a magnetic field that flows out of the page at you. It's coming out of the page at you, okay? Which is interesting because when I go ahead and take a bunch of loops of wire like this, I would get, as I send current into this, if I send current into this loop of wire, it's coming out here, but if I send it in and it's moving around in this way, I can see that inside those loops, as current moves through, I'm going to get a magnetic field straight down. Well, that's pretty interesting because I'm getting a magnetic field through this wire produced this way. I'm basically producing this magnet inside here. And if we go ahead and take an iron core, something made of iron, because irons produce magnets, they have magnetic domains. But if I take an iron core, what I have just made is known as an electromagnet. Which is pretty cool. This is how we make them, right? We get these currents to flow through coils. We have an iron core. With the iron core, it aligns the domains within the iron, and now that iron has become magnetic when it previously was not. This is kind of a sidebar, but this is how the second right-hand rule can tell us about magnetizing iron materials, okay? So second right-hand rule, it tells us the direction of the magnetic field through a current carrying wire. Let's try an example problem. I now have got a circuit. And in that circuit, I have got two parallel plates. These plates are just thin. Maybe they're aluminum. They're very light. And they are separated by a distance of d. Okay? My question to you is this. Will these plates be attracted or repelled from each other when I turn this circuit on? So let's think about this. Let's refresh our brains. We know that both of these plates will produce their own magnetic fields. Let's look at it. Current is going to flow out of the high voltage side into the low voltage side. That's the direction of current. So current is going to flow down this plate, and current is going to flow up this plate. Okay, so that's important. Now, what is the magnetic field produced by this plate? Well, current is down. My fingers will naturally wrap around. So this is going to produce a magnetic field that is into the page over here and out of the page over here. That means anything to the right of this plate will experience a magnetic field out of the page. Remember, I need two things in order for a force to be felt. Back to the first right-hand rule. If I have a charge moving through something, through a magnetic field, a charge moves through a different magnetic field, it will experience a force. Well, guess what this plate is going to experience? This plate is moving through a magnetic field that is out of the page, produced by this plate. These charges, as they slide through, they move through, are experiencing a force as a result of being in this magnetic field produced by this plate. Let's figure out the direction of force this plate will feel. Well, the plate has charges moving up it. And as they move up, using my right hand, the B field is out of the page because the current is up. B field is out, the force is away. This plate will experience an electromagnetic force in that direction as a result. That's the way this plate feels. Let's try it for the other plate. If I get rid of all this, and I say, I wonder what the other plate is experiencing. Well, okay. Let's take it from our picture from the perspective of the other plate. This plate here is producing its own magnetic field. It's got current going up. Outside here, I would have into the page. And then on this side, I have out of the page. That's the magnetic field produced by this plate. Now, this plate is in this magnetic field. So it's sitting in the magnetic field that is produced by this plate. This plate over here produces a field. This plate is sitting in it. Well, I have current going down the page. Current going down the page. I've got a B field coming out of the page out of the camera at you. So current down, B field out. It's going to experience a force this way. This is the force that plate experiences. So are these plates attracted or repelled? Based on where they're sitting with respect to each other in their B fields, it looks like both of these objects feel repelled from each other. Now, they need to be super massless for us to see anything, but they are experiencing outward forces, repulsive forces between the two of these things. Now, you need to be able to use your right-hand rule to figure this out, both your first and second right-hand rules to figure this out. And you need to remember that it's not the B field produced, like this thing doesn't move because of its own B field. This thing moves because it's subject to the magnetic field produced from this object. In order for there to be a force, you need two objects. And in this case, both plates, those are the two objects we have here that produce the electromagnetic force. If you got questions, drop me a comment, send me an email, or ask me in class. Till next time, see ya.